Okay, so here we have the needles from our last experiment, the needles that have become magnetized, right? And we put a little piece of styrofoam on the needle. There you go. All right, we have 2 bowls of water. Guys, put your things in the water.
They both face that way.
Oh, that way.
Very good. Which way do you guys think is north?
That way?
That way. Yes, that's right. So what we've done, so take it and turn it so that the yellow part faces me. Very gently turn it so the yellow part faces me. What do you think is going to happen?
It's gonna go back.
There it is. Yep. No matter how much you do it, it's going to turn it back because we have made a compass. All right. So this is why Petrus Peregrinus used the terms North Pole and South Pole when describing magnets. It was well known before his time that if you floated a magnet in water, like you did in your experiment, one end of the magnet would always point to the Earth's North Pole, while the other end would always point to the Earth's South Pole. So Peregrinus said that when a magnet floats on water, the North Pole is the end that always points north, and the South Pole is the end that always points south. So what's the North Pole of your magnet? That's right, and the South Pole is that way. Very good. All right. The Earth acts like a magnet and attracts one pole of a magnet to its south pole and attracts the other pole to its north pole. As a result, the magnet in a compass turns so its poles are as close as possible to the poles that attract them. However, Earth is a fairly weak magnet. You could have seen that in the second part of your experiment. Even though the needle floated so that one end pointed north and the other pointed south, you could change that by bringing a magnet close to the needle. Oop, let's see if we do that. We didn't do that. All right, what happens when you hold a magnet close to the needle? What happens? Ooh, you can make it sail. How about that? It's like a little ship. Ooh.
Oh, man.
Ooh, you can make it sail. Right? Very good. When you did that, the magnet in your hand attracted the needle more than the Earth did. So the needle moved in response to the magnet in your hand more than the magnet of the Earth. All right, but if you put it back in, what happens? And it turns the same way. Very good. So this was the problem with using compasses in ancient times. According to historians, Chinese inventors had come up with the compass long before then, when Peregrinus was doing his experiments. The problem is that because the Earth is such a weak magnet, it can't force magnets to point in directions of the North and South poles. For example, if you laid the needle you used in your experiment on the table, put it on the table, what happens? Nothing. Turn it this way. Nothing, because the Earth is not that strong of a magnet. However, it's easy to turn a needle that's floating in water. So Peregrinus was the first to suggest making a compass without the use of water.
Look. Because if you turn the magnet another way, you can actually push it.
What?
Come on.
All right, so it does not say what his method of making the compass was without water, but I'm guessing it's similar to the way that we do it today, where it's on, where it can freely spin on like a needle or something like that.
Uh-huh.
Right? So that was good because obviously taking a bowl of water on a ship didn't work so good, did it? Right. That's why they typically used stars
Wait, shut
to navigate instead of a compass until this point.